Welcome guys to another video of propagation of signals in optical fiber. This is under the module 2 and module 2 is divided into two parts, and I'm going to divide further it into two parts. So this will be the first part of 2.1. Let us talk about attenuation. What happens when the signal travels through the waveguide and how much it is going to degrade with lots of different aspects, like maybe due to intrinsic absorption within the material because of extraneous elements or environment. So something like very similar to that. So this is what attenuation is. The performance is degraded because of the lessening of the amplitude, which is supposed to be there from the starting till the end. So transmission loss is the main limiting factor in the optical communication system. This is quite a hindrance when transmission is happening, limiting how far the signal can be transmitted. Transmission loss in the fiber is much less than the copper. When I talk about copper, it is the copper cable. So loss in the decibel can be calculated as 10 log input power by output power. So this is what you need to remember. The formula is going to be there for a few slides here. So Pi by P naught is equal to 10 to the power dB by 1/10 of the power. So you can calculate in reverse also in case it is needed to be found out. Pi by P naught, what is the ratio of the power? So always loss per unit length is calculated. So dB per kilometer is calculated, which is equal to alpha. So alpha is dB per kilometer. If it is supposed to be calculated for L kilometers, so alpha dBl is equal to 10 log to the base 10 pi by p naught. So this is quite a easy formula. Just need to remember what is the attenuation, how much is the length, and how much is uh, the pi by p naught. So this is one problem where you need to remember. This problem is needed to understand how the optical power is calculated. So when the mean power launched into a system of 8 kilometers length of the fiber 120 micrometer, the mean optical power at the fiber output is 3. So the input power is 120, output power is 3. So quite a degradation which is happening here. And how long is the cable or the waveguide? It is 8 kilometer. So what we need to determine is the overall signal attenuation or the loss in decibel through the fiber, assuming there is no connector or splices. So throughout the 8 kilometer length, we do not have any connectors or splices. The signal attenuation per kilometer for the fiber is need to be calculated. The overall signal for 10 kilometers, with the 1 kilometer interval, we have 1 dB of attenuation. I'll come back to that. Second, lastly, the numerical input power by output power. Let us talk about the first one, the overall signal attenuation or the loss in decibel. So as I told you, overall signal attenuation can be calculated using this formula. So 10 log input power by output power, we have the input power as 120, output power as 3 micro. So this is the attenuation, that is alpha in for 16 dB for this overall length, right? So for 8 kilometers 16 dB is the length. So for 1 kilometer, how much it is asked? So for 8 kilometer is 16, 1 kilometer it is 2, which is quite easy to calculate, divided by 8, because alpha is nothing but 16 dB by L. So this is quite an easy task you can perform for calculating both A and B. Now third one actually has something to think about. So instead of 8 kilometer, we have 10 kilometer long link, and there is a splice at every 1 kilometer. So if there is a 10 kilometer length and you need to have splices at 1 kilometer, so how many splices are there? So technically it is not 10, it is 9. You can understand with the help of common logic. If I have to cut a rope of 10 kilometer, 1 kilometer every instance there need to be a cut. So you need to cut it only 9 times, not 10 times. So similar way, you have a 10 kilometer link and splices with 1 kilometer interval, and every splice is going to add an attenuation of 1 dB. So I hope that gives a clear picture. So alpha dB is 2 dB per kilometer. This is the per kilometer, how much is the attenuation. How many kilometers are there? So 10. So 2 into 10 will be alpha L. So alpha L is equal to 20 dB. Now once alpha L is 20 dB, you need to also consider the 9 intervals where it produces 1 dB every interval. So you have 9 into 1, which is equal to 9, so added with 20. So we'll give you signal attenuation of 20 plus 9, 29 dB. Alright, so to obtain a numerical value for the output power, where it is asked in the last case numerical input power by output power in the C, so it is 6 dB divided by 8, sorry, it is Pi by P naught, which is equal to 10 to the power 29 by 10, which I have already shown you here. So this is the 10th power. When I want to calculate Pi by P naught, it is nothing but 10 to the power 29. That is for C they have asked, 29 by 10, that is 10 to the power 2.9, will give us 795 almost, which is equal to the power ratio. Next comes absorption due to the material itself. A major loss factor in is material absorption, dissipation of optical power in the waveguide due to material composition and fabrication. What happens is when you are taking a waveguide, there are certain materials which is used in the waveguide which is actually absorbing the signal. So that is quite unnecessary, but still we cannot avoid it. Maybe we can perform a waveguide preparation where it is made up of superior element, but there are still malfunctions which is happening because of the material itself. So this can be either intrinsic or extrinsic. We are going to talk about both the cases. So there are two types which is having components in intrinsic. Intrinsic is due to the impurities in the glass. So ultraviolet absorption, how ultraviolet signals are absorbed. High energy excitation, that means when the lower wavelength is used, we are going to have a high energy band. And the transformation is high, means whenever low lambda is used, you need to have high power in order to excite the electrons into the higher energy level. So that means you, whenever you are inducing high energy, that means high energy includes high heat, so hence loss is there. Next one, infrared IR absorption. Molecular vibration within the glass creates friction and then creates heat. So this is what the intrinsic absorption is. So it talks about the attenuation spectra for intrinsic loss mechanism in pure germanium oxide and silicon dioxide glass. So this is what the glass material they have used. This is the attenuation dB per kilometer, and this is the wavelength. For what wavelength, what attenuation or how much wavelength is happening, right? So this molecular vibration which is happening is directly proportional to lambda, and high energy excitation is directly proportional to electron volts. Next, let us talk about the other part, that is extrinsic absorption. Due to the waveguide impurities, maybe due to the waveguide impurities, major sources like chromium or copper. So metallic impurities which constitutes the extrinsic absorption depending on the wavelength, of course. So this is why some glasses are colored. So you can have chromium ions which gives you a different color, copper gives you a different color like green or blue or cyan color. They have copper ions thus absorbing some light passing through the others. So you can have hydroxyl ions, that is the OH ions which is present in water. So hydroxyl ion impurities are also a major factor, key factor in generating overtones. Overtones is like echoes which is going to be created when you have a small OH impurity. So this is what the number of attenuation which is having per kilometer, and these are the ions. So cuprous, cupric, ferrous, and so many are there, manganese, so many ions are there. Whenever you are encountering all these impurities, this is the dB per kilometer at this particular wavelength. This is what you need to remember. Okay, this is the overtones which I talked about. So first overtone, second overtone, third overtone. This is again attenuation with respect to wavelength. So this is what the overtone shows. Next comes scattering. We already talked about two parts, that is absorption, intrinsic absorption and extrinsic absorption. Before to that we had attenuation, the lowering of the amplitude. Next comes scattering. So scattering, there are two types. One is linear scattering and non-linear scattering. Let us talk about both. So when some of the power in one propagation mode is transferred to a different mode. So one mode is converted to different mode. Maybe single mode power is converted to multiple mode. So loss of power which is happening. So scattering in glass arises from microscopic variation. You might have very real life example which we can use is a scratched spectacle or a scratched helmet glass, which is going to scatter a lot of light whenever you are driving with a glass which is scratched, maybe a spectacle glass or your helmet glass. It is going to scatter and you are not able to see the light properly. So this is one probable cause for scattering. So inhomogeneities, fluctuations, compositional fluctuations, and from structural inhomogeneities or defects occurring due to fiber manufacture. So this is a probable loss criteria which you need to remember. Next, what are the different types of scattering losses? As I already told you, there is linear scattering, that is output power is proportional to input power and there is no frequency change, thus the power propagated is proportional to the mode of the power. So two types, Rayleigh scattering and Mie scattering, we are going to see in detail. Next one, the power propagation results in frequency change. In linear scattering there is no frequency change. Non-linear scattering there is frequency change. So there are two types, stimulated Brillouin scattering and the Raman scattering. So this is what you need to remember: Rayleigh scattering and Mie scattering. Stimulated Brillouin scattering and Raman scattering are also a very important types of nonlinear scattering. And let us come to the linear scattering mechanism. It causes the transfer of some or all the optical power that contains within one propagation mode to be transferred into a different mode without the change in the frequency. Remember that one mode is converted to different mode with all the power, but there is no change in frequency. This process tends to result in attenuation of the transmitted light, as the transfer may be leaky or radiation mode which does not continue to propagate within the fiber core. Of course, scattering will not let the light will be traveling in the core anymore, because it is obviously going to result in dispersion or it is going to scatter and hence a lot of loss, but it is radiated from the fiber outside to the outside world. With all the linear process, there is no change in the frequency on the scattering. So please remember to mention that frequency should not change whenever there is a mode transfer. Please remember that. Next, what are the different types? Rayleigh's and Mie scattering. So if you can remember, why is the sky blue? Rayleigh scattering is the reason. I will talk about that. So Rayleigh scattering, you have an incident light based on the size of the molecule which is it is going to collide in. So you can see this is very small, bigger and further bigger. So based on the size of the particle, maybe 10 to the power minus 4 micro, 10 to the power minus 1 micro and 1 micrometer, this is the size. So as you are incidenting in this direction, this is a Rayleigh scattering, this is a Mie scattering, and this is Mie scattering due to larger particle. So this is what happens. So Rayleigh scattering, it is going to scatter all towards the same, and then here Mie scattering, whatever the direction it is incident, there it is not going to have a much of a scattering effect, but on the other direction it is going to have a larger effect. Okay, what actually Rayleigh scattering is? So due to the density fluctuation the density of the refractive index of the core or the cladding, we have Rayleigh scattering. Rayleigh scattering is dominant in low absorption windows. For glass fiber, the foremost type of scattering is the Rayleigh scattering. With this process, atoms or other particles within the fiber absorbs the light and instantly re-emits the light in another direction. In this way, Rayleigh scattering appears very much as the absorption, but it absorbs and redirects the light. It doesn't absorb actually, it absorbs from one end and redirects to the other end so quickly that it is considered as scattering. So this is what you need to remember during Rayleigh scattering, and it is one of the very important parts of Rayleigh scattering. And then this is what the figure looks like. So Rayleigh scattering formula is given by gamma r 8 pi cube by 3 lambda to the power 4, and these are the coefficient which you need to remember. So where gamma r is a Rayleigh scattering coefficient, and lambda is the optical wavelength which is used, and eta is the refractive index of the medium, p is the average photoelastic coefficient, bc is the beta c is the isothermal compressibility and at fictive temperature Tf, and K is the Boltzmann constant. So you need to remember this. There is no derivation of the formula. Next comes Mie scattering. So Rayleigh scattering is what is actually causing the sky to be blue, because whenever there is light which is incident directly above the sky or the cloud, there is no dispersion. All the light is going to be falling down. So in the sunset or the sunrise time, there is a small deflection of the light rays which is closer to orange and red. That is the reason why orange and red are going to be taking a diversion or scattering, which is making us feel that during the sunrise and during the sunset, because of the angle of incident of the sun onto the earth surface, we see it as red color or orangish color in the sunrise and the sunset time. Me scattering. So me scattering can be due to the inhomogeneities. Remember that all is dependent on the size. If the size is very less, like as I told you, 10 to the power minus 4 micrometer, we are going to suffer Rayleigh scattering. And if it is 1/10 or lambda to the power minus 1, so this is what happens when we are talking about me scattering. So it is all about the size. Me scattering occurs with the comparable lambda of 1 by 10. Me scattering is very significant, and it can be removed by imperfection removal in the glass manufacturing by increasing delta, which is the difference in refractive indices. So I have given one more table for you to clearly understand. It is non-uniformities, change in the path light, change mode, and hence attenuation. Mode transfer may result in leaky mode, radiation, and hence there is no change in frequency. This is what you need to remember. So in Rayleigh scattering, uniform in all direction. Me scattering, it is not uniform in all direction, as I already told you, as I shown you the figure. Inhomogeneities occur in small scale as compared to the wavelength of light. Inhomogeneities are comparable in size with guided wavelength. So remember that it is 1/10 of lambda. Here it is 10 to the power minus 4, that is lambda to the power 1 by lambda to the power 4 is what you need to remember. This is the formula which I already told you. And intrinsic loss mechanism is low absorption window between IR and UV. Inhomogeneity is due to refractive index variation, which I already told you here, and core cladding refractive index difference along with the fiber length, which is lambda here, that can be increased, and hence if the increased refractive index difference is happening, then me scattering can be reduced. And finally, we have transmission loss factor or transmittivity tau, which is given by gamma r from here and multiplied by length. So this is what Rayleigh scattering is, and me scattering can be reduced by removing imperfection and increasing delta, or coating the fiber. We can increase fiber difference of refractive indices, and hence me scattering can be reduced. So this is what you need to remember. So one figure or one chart which tells everything about linear scattering. Let us talk about nonlinear scattering, that is stimulated Brillouin scattering. Here the frequency is going to be changing whenever there is a change between the mode shifting. So nonlinearity is primarily due to the high power level, high bit rate, and high transmittivity. So the scattered light appears upper and lower sideband, which are separated from the incident light by modulation frequency. The incident photons is scattered, produces a phonon. Remember, phonon and photon are different. Phonons are quantum of energy of acoustic phonons as well as scattered phonons. There are two types of phonons, so acoustic phonons and scattered phonons, based on the frequency difference. What are the phonons which is created different frequency? So acoustic and scattered phonons. So incident photon in the scattered process produces a phonon of acoustic frequency as well as scattered frequency, but it is not going to be the same case in Raman scattering. Here both the cases, both the frequencies are created, that is acoustic frequency as well as scattered frequency. The frequency shift is a maximum in the backward direction, reducing to zero in the forward direction, making Brillouin scattering a mainly backward process. So power in watt can be expressed as 4.4 10 to the power minus 3 d square lambda square alpha dB into V. V is the frequency bandwidth and D is the core of the core diameter, and lambda is the wavelength which is used. Okay. So next comes Raman scattering. So this is a high frequency optical phonons rather than acoustic phonons. Here in Raman scattering there is no acoustic phonons. In Brilliant scattering there is both acoustic phonons and scattered phonons. So you need to remember that. So Raman scattering can occur in both forward and backward direction. In an optical fiber power threshold can be given by 5.9 10 to the power minus 2 d square lambda square. These are the 3 4 formula you need to remember for the Raman scattering power threshold. So I have a chart which is going to tell you about both the cases. Here the change in frequency which is happening becomes significant above threshold power level whenever there is a change in optical power level, and this happens, non-linear scattering happens at high speed, high data rate and high transmittivity. So you need to remember that. So here scattered phonons plus acoustic phonons, here only there is no acoustic phonons, only scattered phonons. So optical power shift varying with the scattering angle. And there is acoustic wavelength which is happening. Here there is no acoustic phonons. So these are the formula, and how you can increase or decrease the power you can identify using the formula. Alright. So here we come to an end of the first part. We will talk about the second part soon.